Well, in our last video, I left you with this question, and now I want to explain how you would figure out the answer to this. And you have a similar question to this in your Mastering Biology homework, and so I didn't want to duplicate it in your lecture quiz. So how do you determine whether whether this forest is a carbon source or a carbon sink? Well, it's very simple. You just subtract the respiration of the herbivores from the net primary production. Remember, and then you get NEP, and then you're going to use this relationship where if NEP is greater than 0, then that means that the ecosystem is storing carbon and it is a carbon sink. So if we look here again, so if we take the net primary production, which is the total, which would be the total amount of photosynthesis minus the respiration of the autotrophs, then we also subtract out the respiration of the heterotrophs, then we're getting the net ecosystem production. And so before the outbreak, this forest had 440 minus 408, giving us more than 0, 32 grams per square meter per year of biomass that was accumulating. But after the outbreak, the net primary production was lower, and also the respiration of the herbivores was higher. And so you take 400 minus 24 and you get a negative 24. So that means that this ecosystem is losing 24 grams per square meter per year of biomass that's being converted by cellular respiration into CO2 and released to the atmosphere. So the question that I had you answer at the end of that last video snippet was this one, and hopefully you came up with NEP greater than 0 means that this ecosystem is a carbon sink, because this ecosystem is taking carbon dioxide from the air. The CO2 is like sinking into the ecosystem and being stored as biomass. Now we want to move into the next concept, concept 55.3. And now that we've talked about primary production, we're going to talk about secondary production. So secondary production is the biomass that is accumulated by the consumers. And so that's secondary production. And then we're going to look at how that chemical energy then gets partitioned by a consumer. How does that consumer use the energy that it is taking in by eating a producer? And then we'll relate that to energy pyramids. Okay, so how does a consumer use the chemical energy that it consumes? You should have a fairly good idea of this after what we learned about animals and how they use the energy that they get. What are some things that a consumer uses the chemical energy for? And hopefully you said that it's going to use some of its energy for cellular respiration because it needs to do cellular respiration to make ATP, which is energy that it needs to carry on its processes. And it's going to use some of that energy to build new organic molecules. So it's going to do biosynthesis with some of that plant material. And that is actually the amount of new biomass that is being stored by this caterpillar, this animal that's eating a plant. And that is the secondary production. And so this is all of the plant material that is assimilated into the body of the caterpillar and then either burned for energy in cellular respiration or stored in that caterpillar's body. But notice that 100 joules of energy are going to be not assimilated. So half of the energy that that caterpillar eats is going to be released as feces or probably as heat due to inefficiencies. So only this 33 joules that is stored as biomass is going to be available to whatever eats the caterpillar. So can you calculate the production efficiency for this caterpillar? It's eating 200 joules worth of material, and it is only producing 33 joules. So what would be the production efficiency? Well, you would take 33 divided by 200, and you get about, I think that's about 15% efficiency. Let's see, maybe I can pull up my calculator and do this math. So I'll pull this over here. We're going to take 33 and we're going to divide that by 200. And that gives us 0.165, or about 16.5%. So when I said 15%, I was ballpark. And so trophic efficiency would be the percent of production that is transferred from one trophic level to the next. And so what do you think is the average trophic efficiency? We saw that for that caterpillar in our example, the trophic efficiency was a little over 15%. You think that's about average for a trophic level? Well, some of you guys who have studied this before maybe know that the average is more like 10%. And so 10% of the energy that is stored by the primary producers is available to the primary consumers. And out of that 1,000 joules that the primary consumers can eat, only about 100 are available to the secondary consumers. So only about 10% of the energy is available to the next level up. So this is what we call an energy pyramid. This is an idealized pyramid of energy. If you were to measure the actual energy transferred from level to level within ecosystems, it would vary somewhat. But this is an idealized pyramid, and it's about average across the world. And so we talk about the rule of 10 in energy pyramids. Only about 10% of the energy is available to the next level up. Well, why are the efficiencies so low? What else have we learned earlier this semester that will give you some clue about why trophic efficiencies are so low? Well, hopefully you thought that the reason that trophic efficiencies are so low is because of the second law of thermodynamics. No energy conversion can ever be 100% efficient, and so you're always losing a bunch of energy as heat. So also, if you look at this, this is why there are so many plants and that there are fewer primary consumers, and that as we go up the trophic levels into secondary and tertiary consumers, we have a lot fewer tertiary consumers, top carnivores, than we do primary consumers, and way less than we have plants. So what we were just looking at is a pyramid of energy. How would a pyramid of biomass compare to a pyramid of energy? Well, in many ecosystems, a pyramid of biomass would be similar to a pyramid of energy. You would have a lot of biomass in the plants, less biomass in the primary consumers, and less as you go up the trophic levels. However, as you know, sometimes you can have more respiration than you have photosynthesis. So sometimes you can actually have an inverted pyramid where you have less biomass in the bottom levels in the plants than you do in levels up above. If you have like a net ecosystem productivity that's less than 0, you will often have not very much biomass actually stored in those producers. So we can sometimes have inverted pyramids of biomass. But by and large, the biomass pyramid is going to look similar to the energy pyramid. So that's the end of our PowerPoint for today, and that's the end of our lesson for today. And I will add another question for you to answer in your quiz.